Log on, tune in, find out. Another good idea from Cambridge.
Robin Collins is Professor and Chair of the Department of Philosophy at Messiah College, Grantham, Pennsylvania. He received his PhD in philosophy from Notre Dame, if I'm pronouncing that correctly, in the US, and has graduate training in theoretical physics as well. He is very interested in this whole issue of cosmic fine-tuning. He's running a summer school and a 5-day workshop on that issue in the University of St. Paul, Minnesota, St. Thomas University in St. Paul, Minnesota, in the summer. He's got a couple of books coming out on that that he's still preparing, and also chapters in books we have had on our bookstall, Bernard Carr's book and a book by Neil Nance on design and so on. So it's tremendous you've been able to be with us, Robin. Really tremendous, because it's sort of a little bit short notice. We're immensely grateful. Looking forward to what you have to say. So thank you.
There's been a slight change in title to Cosmology and Fine-Tuning 3 Approaches. And it will mostly be dealing with the philosophical issues. And the habit of philosophers is to read papers. So I'll be reading a paper with the PowerPoint just to help you focus on the various sections I'm at. So there's only about 12 PowerPoints. In this paper, I will suggest 3 approaches to cosmic, or I will discuss 3 approaches to cosmic fine-tuning. In the final section, I will suggest how belief in God can have a positive impact on scientific practice, particularly in the area of cosmology, just as it did for Lemaître in coming up with his theory of the primeval atom, or Big Bang theory, or Cantor in coming up with the set theory. The anthropic fine-tuning refers to the claim that the laws of nature, the constants of physics, and the initial conditions of the universe must be set to an enormous degree of precision for embodied conscious agents like us to exist. So we have a couple of slides for that. This is from a student when I first started thinking about it. I used to draw the constants, the values as dials. If they're perfectly set, there can be life.
Almost perfect.
Yeah, or almost perfectly. Dials imperfectly set, no life. That's the fundamental idea. 3 major responses have been offered to this fine-tuning: the multiverse explanation, theism, and the claim that it is just a brute fact that requires no further explanation, a view which I call single universe naturalism. I will start with the multiverse explanation. The multiverse explanation of fine-tuning begins with the multiverse hypothesis. This hypothesis claims there are a very large, if not infinite number of regions of space-time with different values of the constants of physics, different initial conditions, and perhaps even different laws of nature. It then claims that in a sufficiently varied multiverse, it is no surprise that some universe is observer structured. That is, structures that observers will arise in it. Finally, it invokes the so-called observer selection principle, which is the tautological claim that embodied observers can only exist in a region of space-time that allows them to exist. This renders it unsurprising that as observers, we find ourselves in an observer-structured region of space-time, since it is impossible for us to exist in any other type of region. That's a little out of order, I think. So that should go, and I'm going to go back to the previous one. The observer selection principle is essential to the multiverse explanation because it prevents it from undercutting the need to explain other seemingly surprising events and features of the universe. For example, normally one would think that it is too coincidental for a 6-sided die to land 50 times in a row on 4 just by chance. So you'd seek an explanation for it. Yet in a large enough multiverse, someone will observe this to happen. Nonetheless, it is still improbable that a randomly selected observer will see such an occurrence. Hence, purportedly, the multiverse hypothesis combined with the observer selection principle can render it unsurprising both that we exist and that we find ourselves in an observer-structured universe, while at the same time not undercutting ordinary claims of probability. Elsewhere, and that goes back to the previous slide, I have argued that by far the most popular versions of the multiverse hypothesis, namely those that postulate the multiverse was generated by some physical process, push the problem of fine-tuning up one level to the laws required to generate the multiverse, as you see here, has to be well built. For, I argued, in order to generate even one life-permitting universe, this process must be governed by precisely the right set of laws. And now I pursued that argument in Bernard Carr, The Multiverse volume. Here I want to briefly outline what I believe to be perhaps an even more powerful objection to the multiverse explanation, one that applies to any type of multiverse. The objection begins by noting that the universe is not fine-tuned so that observers can exist. Rather, it is fine-tuned so that, at least within some epoch, the predominant kind of observers that exist, that are likely to occur, are embodied conscious agents that arise through an ordinary evolutionary process and that can interact with each other. Indeed, it appears to be fine-tuned so that those embodied conscious agents can develop technology and discover the universe, something I will briefly touch on later, but have developed more fully elsewhere. Now we go on to the next slide. This will be for a while. This one will be up. I will call universes structured for the existence of such agents agent-structured universes. The difference between a universe being merely observer-structured and agent-structured is well illustrated by the much-discussed Boltzmann brain problem that arises with respect to multiverse explanations of the low entropy of the universe. A Boltzmann brain is a localized fluctuation in mass energy that has the right organized complexity, such as the kind of complexity exhibited by brains, to qualify as an observer, at least assuming a view in which the mind supervenes on certain complex organizations of material processes, such as reductive materialism would be an obvious example of that, where minds are just reduced to material processes. BBs, as I'll call Boltzmann brains, as Don Page introduced, terminology, do not arise through a normal evolutionary process. Outside the local regions of space-time in which these fluctuations occur, the universe is in a high entropy, chaotic state. These fluctuations that give rise to BBs can be momentary and small scale, just enough for a conscious experience of observing the immediately surrounding region of space-time, or long and very large scale. Apart from special constraints on the entropy, under the usual canonical probability measure of statistical mechanics, the probability of such a fluctuation occurring is always very, very small, and rapidly decreases with the size of the fluctuation. By far the most probable fluctuations, therefore, are of momentary isolated observers with chaotic experiences. Even for fluctuations resulting in a community of interacting agents, the most probable fluctuations will be a community that experiences the rest of the universe as being chaotic. Because BBs have a finite probability of occurring in any region of space-time with a positive energy density, or even in a vacuum, in a sufficiently large universe that has some lower bound to its mass energy density, many BBs are almost certain to occur. This is true even if the constants and parameters of physics are not fine-tuned. For example, if the dark energy density is too large for galaxies and stars to form. Furthermore, in standard versions of the multiverse, such as promoted by Alex Vilenkin and Leonard Susskind, the bubble universes that are produced are infinite in size and meet this minimal mass energy condition. Such infinite universes will have an infinite number of BBs, whether or not their constants are fine-tuned. The existence of these BBs in non-fine universes show that the constants and parameters of physics are not fine-tuned for observers, but rather for embodied conscious agents that arise through a standard evolutionary process. Yet, because of its reliance on the observer selection principle, the Earth hypothesis can only take away the surprise or explain that our universe is an observer-structured universe, not that it is also agent-structured. Even though I have above I invoke the usual probability measure of statistical mechanics, my argument does not depend on that measure. It only depends on the much weaker claim that the constants do not need to be fine-tuned for universes to have observers. And this claim only requires the assumption that many BBs will occur in a sufficiently large universe with minimal mass energy densities. Given this assumption, being observer-structured can no longer be equated with being agent-structured. And consequently, without additional postulates, the multiverse hypothesis will fail to account for the fine-tuning. In response, a multiverse advocate could postulate that, contrary to the usual measure, there is a true probability measure that will make it likely that a generic observer will find itself in an agent-structured universe. In this case, however, the work of explaining the fine-tuning is being done by the right choice of probability measure, not the multiverse hypothesis. Accordingly, it is unclear how multiverse advocates do better than single universe advocates in explaining the fine-tuning. For example, in an attempt to explain the fine-tuning, the latter could also postulate the existence of the right probability measure, namely one that gives a significant probability to the existence of an agent-structured universe. Further, in both cases, the problem of fine-tuning is likely to be kicked up one level to that of the right probability measure itself, one that puts a significant probability into the teeny, as we see here, the teeny agent-structured range instead of elsewhere over here. Another response multiverse advocates could present is to build into the definition of the relevant kind of observer that is part of a community of interacting agents, or comes about through an evolutionary process. The problem here is that one can always do this for any attribute of the universe, thus making it certain that a generic observer will observe that attribute. This would undercut ordinary claims of improbability, such as the case of the die mentioned previously. Moreover, since the usual measure implies it is much more probable for such a community to exist as a small bubble, with the surrounding universe being in a high entropy state, this response does not account for why we observe a relatively low entropy throughout. There are two key ways in which the above way of framing the problem that BBs present provides a different and arguably more powerful way of understanding the problem that BBs present and found in the literature on the topic. First, in the literature, the BB problem is typically raised either concerning multiverse explanations of the low entropy in the universe, or as a pesky untoward consequences that arise with multiverse explanations, or certain types of universes that expand forever. It is taken as given, however, that the multiverse can explain the fine-tuning of the constants. This gives the impression that if we can find some way of explaining the low entropy of the universe, or avoiding these pesky problems, along with and avoiding the predominance of BBs in that explanation, then the multiverse explanation will have succeeded. My analysis, however, shows that even this will not bring the multiverse to square one of explaining the fine-tuning of the constants. The reason is, as long as non-fine-tuned universes contain large numbers of BBs, our universe cannot be said to be fine-tuned for observers, but only for the kind of agents that arise through the normal evolutionary process. Thus, the multiverse will not be able to explain the fine-tuning. Very large non-fine-tuning universes, however, will contain many BB observers, even if there is some special, yet to be discovered laws that imply that generic universes will have low initial entropy. Second, unlike the standard BB problem, the above problem only requires the assumptions that BBs will exist in a sufficiently large universe with a minimal positive energy density. It does not require any assumption about how likely BBs are relative to non-BB observers. So there's no measure, I don't have to invoke a measure beyond that assumption. The above analysis shows, I believe, that the reason the multiverse seems to offer an explanation of the fine-tuning is that the actual agent-structured fine-tuning has been mistakenly conflated with the non-existent fine-tuning for observers. It's very much the same as somebody mistaking observers with human things that just look just like human beings. Further, it shows that to get the first step of explaining the fine-tuning of any of the constants, the multiverse advocate needs to invoke some special probability measure that makes it likely that a generic observer will find itself in an agent-structured universe. This, however, is likely to merely transfer the fine-tuning problem to that of having the right fine-tuned probability measure. Finally, it should be noted that the existence of these BVs also undercuts the so-called weak anthropic principle objection to the fine-tuning argument, commonly stated as, if the universe were not fine-tuned, there would be no one around to observe it. This objection also suffers from the above problem since observers do exist in non-agent structured universes. And I should say that I'm not actually opposed to the multiverse hypothesis. This is only saying it doesn't explain the fine-tuning. I think under theism, it's likely God would maybe create many universes. So I'm not opposed to the hypothesis itself, only as an explanation. The next section is on the theistic explanation. Slide here. In contrast to the naturalistic multiverse explanation, theism does render it unsurprising that an agent-structured universe exists. To begin, we would expect an all-good God to create a reality with at least a positive, if not optimal, balance of good over evil. Thus, arguably, theism should lead us to expect a universe structured for the realization of moral and aesthetic value. Given that we can glimpse some special value that highly vulnerable and body-conscious agents like us can realize that could plausibly be thought to outweigh the evil, such as the suffering involved, that result from such embodiment, it follows that it is not surprising that God would create an agent-structured universe. I propose that one such value is the ability to engage in particular kinds of virtuous actions, such as self-sacrificial love, courage, and the like, but the vulnerability that comes from embodiment allows. In a theodicy I've developed elsewhere, it's coming out with the Blackwell Companion and Problem of Evil, I claim that these actions allow for eternal connections of appreciation, contribution, and intimacy between conscious agents. For example, if someone significantly helps me in times of suffering, it can create a connection of appreciation in me that has the potential of lasting all eternity and hence growing in value. And the main point there is we can glimpse some reason why God would create a universe like ours. That renders it unsurprising, just to be able to glimpse that. Next, I want to look at single universe naturalism. That's the third approach. Single universe naturalism does not purport to explain the fine-tuning, but instead claims that an agent-structured universe is a brute, inexplicable fact with no further explanation. This version of naturalism is often presented, as naturalism is post-theism, I should explain that, and any other supernatural or any other kind of cause of the outside, transcendent cause of the universe. This version of naturalism is often presented as being based on an unwillingness to go beyond what the evidence warrants, not based on an alternative faith commitment. For example, that's how it's presented in Atheism, a very short introduction at Oxford University Press. In contrast, I will now argue that even apart from the fine-tuning evidence, naturalism, whether of a single universe or multi-universe variety, involves a faith commitment regarding the structure of reality as great as that of theism. As I will argue in the last section of the paper, these different faith commitments can lead to significant differences in one's scientific methodology in certain areas. I begin with what has become known as the underdetermination of theory by data problem. This is the problem that for any set of extant observational data, there is always an indefinite number of logically consistent hypotheses that can account for the data, but which have different predictive consequences in untested domains. Consequently, in order for scientists to choose one theory over another, even merely for its potential predictive success in unobserved domains or new applications, scientists must go beyond mere logical consistency with data. Rather, they must rely on what I call theoretical virtues, The most commonly cited theoretical virtue is that of simplicity, a virtue that says that everything else being equal, we should prefer simple theories over complex ones. Using this virtue commits one to a claim somewhere in the neighborhood of the idea that the relevant aspects of the universe, such as the fundamental laws of nature, are more likely to be simple than complex. The need for invoking simplicity is nicely illustrated by the case of curve fitting. Curve fitting, in which scientists attempt to find the right equation that both accounts for a body of data and can serve as a trustworthy basis for future predictions or extrapolations. For example, suppose that one collects data on the relation between the magnitude of force exerted on a mass and the magnitude of the mass's acceleration. The data will consist of measurements of accelerations that result from various forces. Graphically, this could be presented by a plot of data points with error bars, with the amount of force on the y-axis and the amount of acceleration on the x-axis. It is a mathematical fact that for any number of data points, there always exists an infinite number of functions that will perfectly go through the data points, but radically disagree about the values of the force associated with unobserved values of acceleration. Like over here. They disagree over here, they all go through the data points though. Consequently, to choose the appropriate function to use for prediction, scientists must consider something more than fit with data and logical consistency. Typically, scientists consider the simplicity, naturalness, or some other purported feature of an equation, such as how well it fits with background information, previous theories, or similar cases. Indeed, the equation they ultimately choose might even miss one or more of the points by a greater amount in experimental error. In the terminology I will now introduce, the use of theoretical virtue implicitly commits one to claiming that some property is what I call an ideal of natural order. Roughly, I define some overarching problem as an INO for a person, ideal of natural order, for a person, if and only if, one, the person is explicitly or implicitly committed to the claim that the world is, or likely to be, structured in such a way that there is a positive realization of that property, such as simplicity. And two, that commitment guides their inductive practices in the choice of theories. For example, the use of simplicity in science does that. Thus, insofar as scientists use simplicity to choose theories in inductive practice, they are committed to simplicity being an ideal of natural order. Finally, I define a primitive ideal of natural order, a PINO, P-I-N-O, as an INO for which one has no further explanation in terms of another INO. There. As shown by the curve-fitting examples, INOs form the basis of our inductive practices, namely being able to extrapolate from observed data and in choosing the best explanation of some set of phenomena. This means that one's primitive INOs cannot be justified by their past success, since any argument from their past success to their future reliability would be an argument from observed data, namely their past success, to unobserved data, namely their future success, and thus would require assuming the PINO in question. Nonetheless, one should require that they be consistent with their past success. In general, naturalists and theists share the same INOs, with some qualifications to be discussed below. Where they differ is in their PINOs. Consider simplicity. Both theists and naturalists would accept simplicity as an INO. Non-theists would likely take that INO as primitive. It is a brute fact that the universe is structured in a simple way, and it is a brute fact that simplicity should be an epistemic norm to decide between scientific theories. In contrast, theists are committed to saying that God has structured reality for a positive realization of moral and aesthetic value, God's fitness. Therefore, the commitment to non-contingent divine reality being structured in this way constitutes theism's PINO. a theist could then explain the success and normativity of simplicity and elegance in scientific theory choice in terms of this PINO. In the case of simplicity, one such explanation is that simplicity contributes to elegance, at least with the classical notion of elegance as simplicity with variety, famously stated by William Hogarth in 1753. Thus, for this reason alone, theism renders it unsurprising that an elegant universe has a high degree of complexity while having a highly simple underlying law structure. Further, this complexity is necessary for embodied conscious agents, explaining why the universe is not even simpler. A theist could also argue that certain moral goods can be more fully realized in a world structured for scientific technology and discoverability, and ordinary discoverability of the world. They could then go on to argue, as I will below, that the universe manifesting the right kind of simplicity greatly aids in its discoverability. For instance, with regard to the first point, technology allows for embodied conscious agents to influence each other for good or ill on a much larger scale, thereby greatly increasing the range and extent of potential virtuous responses and virtuous connections between these agents. In addition, one might think scientific discovery is important in and of itself as a good. So we can glimpse a reason for God creating a discoverable world. My analysis so far can be summarized as follows. Theists must make a leap of faith in believing in God. But since God's existence can plausibly explain why we should trust our theoretical and inductive practice, theists do not have to make an additional leap of faith in the continued reliability of these practices. On the other hand, in order to engage in empirical inquiry, such as science, naturalists must make a leap of faith in their continued reliability of the INOs they use. Consequently, apart from other considerations, there's a stalemate of one leap of faith versus another. Arguably, the fine-tuning data tips the balance in favor of theism, but that is not all. I will now argue that the use of simplicity in scientific theory choice implicitly assumes that the kind of simplicity exemplified by the universe is one that makes it scientifically discoverable for the embodied conscious agents that arise in it. And this ends up building in a teleological assumption that is highly problematic for naturalism. Specifically, the kind of simplicity that has been successful in science and is now implicitly considered normative is simplicity in the humanly practical limit, not absolute simplicity or elegance. Example coming up here. To illustrate, consider Newton's equation of gravity. F equals g dot dot dot. This equation is very simple when written in the Newtonian framework, namely one based on Euclidean geometry with its 3 spatial dimensions and 1 independent time dimension. Similarly, Einstein's equation of gravity has great simplicity when expressed in the mathematical framework of general relativity, namely a 4-dimensional semi-Riemann manifold. Yet if one wrote Einstein's equation of motion in Newton's conceptual framework, one would obtain Newton's law, F equals that, plus an infinite number of small correction terms. These correction terms would only become important for large gravitational fields or relativistic velocities. Yet they exist, and hence within the Newtonian framework, the experimentally correct equation of gravity is actually enormously complex. Its simplicity lies in its humanly practical limit, being where we are around the sun, not being in these other circumstances. Furthermore, the fact that it has such a simple limiting form for practical purposes depends on specific contingent facts about our existence. For example, that our planet is not orbiting close to a black hole. Thus, it need not have been that way. Similar things could be said about the relation of quantum mechanics to classical mechanics. If the predictions of classical mechanics in terms of quantum mechanics in terms of expectation values are written out in the classical mathematical framework with real numbers denoting quantities, one obtains simple equations corresponding to the equations of classical mechanics, with an infinite number of correction terms that are very small except when quantum effects become important. This simplicity in the humanly practical limit, which I will henceforth call qualified simplicity, has allowed us to discover the classical equations while at the same time providing the experimental basis for moving to quantum framework. To make sense of the continued use of this qualified simplicity, one cannot merely assume that the underlying law structure of the world is likely to be simple or elegant. Neither of these would give us any grounds for thinking that the equations of physics would be simple in humanly accessible limits within ultimately unsatisfactory mathematical frameworks, such as the Newtonian framework, but not simple outside those practically usable limits. Being structured for discoverability, however, does make sense of it. Given our limited cognitive capacities, natural selection would favor creatures that prefer simplicity over complexity. Thus, if God wanted to make a universe optimally discoverable, it would make sense for God to structure the world so that one, at each conceptual level, such as the flat space-time of Newtonian mechanics, simplicity would offer a generally good guide, but it would fail at the boundaries, therefore forcing the embodied conscious scientist in that universe to go to the next theoretical run, such as the curved space-time of Einstein in their scientific quest. This use of qualified simplicity is an example of a more general implicit assumption made in scientific practice, namely that the world is structured for discoverability. Philosopher of physics Mark Steiner has pointed out many cases of this implicit assumption in the development of physics in the 20th century. Although naturalists might implicitly make this assumption, it is one that is difficult to reconcile with naturalism's anti-teleological commitments. And I should say that would be a practice in current physics, who most don't consider we're in the correct conceptual framework, so that there's some we're in a low energy approximation. And so likely our equation is going to be like going from Newton to Einstein when we go to the next level. So we're really using simplicity in the practical accessible limit in the current physics. Next, I will consider how whether one adopts the theist or naturalist, PI&O can make a difference in one's scientific practice, particularly in the area of cosmology. I will start with the theist PI&O. Historically, the belief that the universe is aesthetically structured at some basic level strongly influenced the practice of physics from the scientific revolution until today. As Morris Klein, one of the most prominent historians of mathematics, points out, from the time of the Pythagoreans, quote, from the time of the Pythagoreans, practically all asserted that nature was designed mathematically, end of quote. Of course, in Christian Europe, this notion of a mathematical design to nature was motivated by theism. Two of the most prominent advocates of such a view being Galileo and Kepler. Both claim that their physical speculations were guided by a belief in God as a great geometer. Although often no longer grounded in theistic belief, this tradition has continued into the 20th century, with Albert Einstein being its most prominent advocate. Indeed, Paul Dirac famously took this to maybe to an extreme of saying it is more important to have beauty in one's equation than to have them fit experiments. Further, as discussed above, belief in God can provide a confidence that the universe is structured so that we can discover it, a confidence that has been amply confirmed by the success of science. This boost in one's confidence in the universe's discoverability resulting from theistic belief can have a significant impact on one's scientific practice. To begin to see this, consider the commonly raised objection to the fine-tuning argument that there are some features of the universe that seem irrelevant for life. For example, cosmologist Sean Carroll states that there is a better reason to be skeptical of the fine-tuning claim, that's a quote here, the indisputable fact that there are many features of the laws of nature which don't seem delicately adjusted at all, but seem completely irrelevant to the existence of life. So what are these? Well, Carroll, Mario Livio, Stephen Weinberg all raise one specific example in common, that involving the extra generation of quarks and leptons. Here's Carol. All of ordinary matter in the universe seems to be made out of two types of quarks, up and down, and two types of electrons, electron and electron neutrinos, as well as the various force-carrying particles. But this pattern of quarks and leptons is repeated threefold. So yeah, this one, these, over all these columns here. The up and down quarks are joined by four more types, just as the electron and neutrino are joined by electron-type particles and two more neutrinos. As far as life is concerned, these particles are completely superfluous, so only these play a role in life right here. Although it is not clear that God would have to create every element in the universe to serve a purpose, nonetheless, a theist would be motivated to search for a way in which such features did serve a purpose. For example, in the case of these extra generations of quarks and leptons, a theist would be motivated to search for another reason, such as the generations being a necessary consequence of some deeper, more elegant theory, or being indirectly necessary for life, or necessary for discoverability. In this case, theistic belief motivates a search for a deeper set of laws or principles that manifest such a purpose, with the seemingly irrelevant particles, in this case, providing important clues. Indeed, in the above example, the three generations fall into a fairly neat symmetrical pattern. For example, the particles in the first row are identical, except for mass. This gives us reason, independent of theism, for thinking there is some elegant underlying theory that explains their existence. Further, the three additional particles have a low enough energy that we can detect them. If the tau particle, for instance, was much larger, we would not have discovered the symmetrical pattern. Here's the tau right there. It's quite large. No, here it is. That's the one right there. That's not the tau, it's the other one that's really large. Sorry, that's wrong. Thus, arguably, their masses are just right to motivate us to look for a deeper theory. This further reinforces considering them to be clues. Interestingly, in this case, atheism ends up being, or at least that kind of atheism, ends up being a science stopper, encouraging us to accept that there is no deep reason for the extra generations, whereas theism encourages the search for a deep explanation. The atheist objection commits what could be called the ungodly appeal to gaps fallacy. As some theists in the past appealed to gaps in our scientific understanding to argue for God's intervention in natural affairs, these atheists appeal to gaps in our understanding of how these features contribute to the value of optimality of the universe to argue for the non-existence of God. As another example, consider the so-called anthropic, so-called cosmic coincidence problem in current cosmology. That is the fact that at present the dark energy density is approximately that of matter radiation energy in the universe. And I forgot my slide was supposed to be, but there's a bunch of other examples I have. This is kind of that-worked out set of slides. Although a considerably larger dark energy density would probably not allow for galaxies to form, a smaller value would not be detectable. Further, it seems that a zero value for dark energy would be more elegant. Given this, a theist should be motivated to think that the detectable dark energy is likely to serve a role in discoverability, such as being a clue to a deeper theory. And also, very related to that, I just have a little time here so I can mention something related to that problem. Anthony Ordero has argued in Cold Big Bang Cosmology is a counterexample to the Anthropic ideas, that if the photon to baryon ratio, which gives you the level of cosmic microwave background radiation, were much smaller, so those would be cold Big Bangs, you have a vastly larger region of parameter space in which life could occur. So he thinks if you just use anthropic fine-tuning, it's really surprising we're in the region we are in with a high photon to baryon ratio. But it's not surprising if you include discoverability, because that cosmic microwave background radiation is just large enough to be usable. If it was much smaller, like on order of 10 or the order of 100 smaller, it would be much less optimal. So it seems to be not too large. If it's too large, there's problems with life forming, but not too small either, in the right region. So it makes sense under this discoverability idea. So where I just want to make sure that, okay, there we are. Further, it seems that a zero value for the dark energy would be more elegant, so I've already read that. We'll go to the next thing here. Similar things could be said about, excuse me, okay, down one. My analysis above implies that naturalists and theists have different stopping points for what they consider a satisfactory scientific explanation. Stopping points corresponding to the respective PINOs. Atheists will be satisfied if they can appeal to some simple or perhaps elegant ultimate explanation that does not commit them to any appearance of teleology. Thus, they will attempt to explain away any features that appear to be teleologically ordered. One sees this in atheists such as Richard Dawkins and Peter Atkins. Peter Atkins, for instance, advocates a bare bones view of the world, seeing this as the one demanded by the ideals of science. This also leads to a preference for severe sorts of reductionism among naturalists, because it just gets the simplicity, the ultimate simplicity of everything. Eliminates any need for teleology, so they think. In contrast, theists see a teleological ordered structure of laws of initial conditions as the final stopping point of explanation. Whether that structure is one that maximizes elegance, provides an optimal environment for the formation of embodied conscious agents, or optimizes the ability of those agents to engage in science or something else. Consequently, each has different methodological implications for what needs an explanation. When we should search for a deeper theory and what that deeper theory might look like. Theists who reject the God of the gaps will seek scientific explanation for causal gaps in the universe, since generally such gaps decrease the universe's elegance, but not for teleologically ordered structures of laws of initial conditions, unless they can glimpse a way in which a deeper theory might be more value optimal. Further, they will search for explanations of any basic structure of the universe that appears to conflict with their PINO, such as one that appears to take away from the elegance and discoverability of the universe, while at the same time seeming to serve no other purpose. Thus, for instance, theists will see much less need to offer a scientific explanation of the seemingly enormous, improbable initial configuration of mass energy at the beginning of the universe, though they still might have some motivation to find an explanation in terms of some more fundamental laws, since arguably this would be more elegant. So I think theists have some motivation to seek for explanation of the value of the constants in terms of a deeper theory, because that would increase the elegance of the universe. And then the deeper theory would reinstantiate, I think, the fine-tuning. If you had a deeper law that was the original hope of string theory that would entail the value of the constant, then that would reinstantiate the fine-tuning at the level of laws. But it would be more elegant, so I think theists should think that that might very well be the case. On the other hand, since as noted above, many of the particles in modern physics appear to serve no life-limiting role, the theists will be motivated to seek an explanation for them in terms of a deeper theory that brings out their overall contribution to the aesthetic and moral value of the universe. In contrast, as we saw above, atheists will be less motivated to seek a deeper explanation, especially those who use the existence of these particles as evidence against God's existence. So in these ways, whether one is an atheist or theist can make a difference in one scientific practice at the forefront of physics. And just something I want to say in addition to that, I have two ways, I think I put it on the slide here. The positive influence of theism, I think we have Lemaître with theism allowed him to entertain new possibilities. I think that's what's going on there. And I think the same with Cantor with the infinite set theories. So here it served a positive role. The non-theists were rejecting these, that the universe was the beginning. That theism allowed one to entertain that as a serious possibility. In other cases, like Kepler, Galileo, Newton, theism influenced their ideals of natural order, that the universe would be structured in a mathematically aesthetic way. So that's pretty much, I have additional stuff, but I do want to leave time for questions. So that's the end of my talk. There's additional stuff here and examples of discoverability, other examples. But I think I could answer questions about that. So.
Over to you, folks.
On that last thing, I'm a little curious because, Raphael Busso has explanations for this coincidence thing. And he doesn't, when I talk to him, he doesn't have explanations. So,
Well, I'm not denying other people can have explanations for the cosmic coincidence. I'm just saying that theists will have another tool for an explanation like discoverability.
but you seem to have the idea that they wouldn't see. I'm not much of a particle physicist, but I would have certainly guessed that atheist particle physicists would be seeking some explanation of why three generations.
I only said they would be less motivated. I don't deny that they would, and they maybe should on aesthetic grounds of simplicity.
Right.
But if they're using it, just like theists, so there's a kind of equivalence of God of the gaps here going on. Just like theists have attempted in the past, falsely attempted to appeal to the gaps in our scientific understanding to argue for God, and that has inhibited science, it's been bad. Atheists are doing the same counter move, trying to use these particles, and Weinberg mentions them, it's mentioned over and over again, it's sort of a devastating critique of there being a God or fine-tuning the existence of these extra particles. And I'm saying when you do that, you're committing the ungodly appeal to gaps, and that is stopping science. But you could be a more reflective atheist about those and say, well, maybe I also have aesthetic grounds for appealing to something deeper.
Right.
Thank you.
So I don't really, it might have seemed like I denied that, but I did, really.
Yeah.
I did attend to it.
Great. Bill Carroll.
I have sort of two questions which are connected by what seems to me an absence of philosophy. In other words, you set the opposition between a theistic approach, and the question of the naturalist approach.
Right.
And you say that if you have the theistic approach, you have all these beneficial features of what can happen with science as well. If you take natural philosophy in the Aristotelian tradition, which talks about things having natures and characteristic behavior and an elaborate teleology, one could make a very similar argument that by being a natural philosopher in the tradition of Aristotle, that's certainly a much more productive way to be committed if you're going to be a scientist than to be a denier of that tradition. I'm troubled that you think that to say the example of single universe naturalism, that the universe is a brute fact, that's a position of faith. I would say that's a philosophical position. And I'm troubled throughout a number of people's presentations that using the word faith in so many different senses. In other words, to say that the universe is just a brute fact is to affirm a first principle of metaphysics, not a principle of faith that is anything like faith in a theological sense.
I would agree with you. Let me just agree with you that the faith there, I leave it undefined, and so all that needs to be cashed out more. I mean, it's a short talk.
Right.
So that needs to be elaborated more, and what I mean is kind of the common sense use of the word faith, that it's a commitment that you can't further justify. So it's a kind of choice you might make metaphysically. And so the atheist often, like in the short introduction to atheism, and he will use the word faith, they often use that in that way, is a commitment to entities or grounds of being or causes, ontological causes, however you cash out belief in God, that is not justified by any epistemic, valid, recognized epistemic method. So there's a sort of just taking the data and our normal methods of inference for what they give us and not going beyond that. And I'm saying, no, they do go beyond that. They have to engage in inductive practices. So that's my real point, not the point about what faith is. That's just a shorthand that I'm using. And so that point's well taken.
Well, what about the problem here, it seems to me, is a position of natural philosophy, not a problem of theism versus naturalism, but the problem of getting an adequate natural philosophy which concerns questions of purpose and order in nature. That's a question of natural philosophy, not so much a question of theism. Or at the very least, it's first a question of natural philosophy before it becomes an issue of theism.
Let me just quickly say something in regard to that, because in a longer version, in another paper where I use some of this material, what I actually do is go on into the question. It's really the changes between, not theism, it's not so much theism, but it's two PI notes. One is that the reality is structured for the positive realization of moral and aesthetic value. That could be held outside of theism, for example, by Plato. It's structured in accordance with the good, right? So you could hold that outside of theism, and then you have the other PINO for the typical naturalist. The naturalist could have that, but the typical Western naturalist is morally indifferent. It's at best structured in accordance with elegance. So then I say those are at the same ontological level, okay? And that's where the two, it's a choice there. You can't say initially one choice is better than the other, apart from the fine-tuning and things like that. Then I go on to say theism adds a couple other claims, like the ground of that structure is some unified being that's more appropriately described as personal instead of impersonal. So that's the elaborated version that I think maybe addresses your question.
Thank you. Any more questions? Peter?
Following up your point, there are a lot of unbelievers who tacitly say that nature is structured for aesthetic values because it's aesthetic theories that have such a lot of value. And they could be challenged on that one, and probably are. But within your framework, you have a means of sort of ordering this. It's probably the moral values.
The moral values is the key difference. So if there is a kind of move. I mean, it's a halfway house to go up with elegance, but they seem to feel they need elegance. But what they're really unwilling to go to is it's morally indifferent. So it might be elegant, but their elegance already has a sort of, it's very close to moral values, and that's why, goodness and beauty meet, in Plato. There's something very close about the two. They're considered a good, those sorts of things. So there's already a move in that direction a little bit, but they don't want to go to the next one of goodness, moral goodness.
Yes, back.
I have this idea of a series of almost breadcrumbs that God leaves us to bring us towards discoverability. So a certain level of nature that can be probed using 17th century technology, not too far beyond our grasp. Might there also be criteria for the end of science? Perhaps God does not want us to keep on probing the levels of the universe indefinitely because he would give us too much technological power. And the next level of mathematics below what we have is just too hard for our brains. How would a good God give us a sign that this is as far as we go, no more? And is there a difference between what you have in the universe without it?
Well, maybe leave that to a prayer request. How would a good God leave such a sign? I mean, it just might, you might have things just peter out. It might just be we can't make any further progress. And it just kind of stalls out. And we eventually turn to something else. Maybe it's the case that there's another, maybe it could be the case at the frontier of physics. Eventually you have to get to such high energies, you can't build accelerators inside of the solar system to test them. We've been fortunate we can test some of this stuff cosmologically. But it might peter out soon in the future. Maybe there's another frontier we could open up, or maybe we have to do some other activity. Whatever its purpose was for being there has been accomplished. So I mean, I would be open to those possibilities.
Thank you. Any more questions? Yes.
Well, going back to these observer brains, surely they would need to be able to perform experiments to gain experience and develop ideas through much communications and so on. So that's what I'm really saying. The idea of an individual observer or unique is a little bit of a fallacy.
So whether Boltzmann brains could really be observers is your question?
Without being actors at the same time, yeah.
Part of that presses a problem with multiverse hypotheses themselves. What is an observer is very vague and unclear. What kind of, when they say observer selection, which they need, what are we talking about in being observers? I understand Don Page is some minimal conscious experience, maybe an experience moment of self-consciousness. And then if you're a reductive materialist, for instance, then you would think these could have that. There'd be these just a lot of observer moments. And then, at least under the usual measure of the probability, you could actually get these fluctuations, be very, very rare, but in the infinite universe they're going to happen, which even has very rarely, some of them would be communities, like what you say is needed with memory traces, and yet the rest of it, outside this local bubble, you would have chaos, which is not what we observe. We observe a universe that's not chaos that we could probe. So that's where the discoverability issue comes in play.
Related to that, I think, is this argument of Penrose about the initial entropy and the 1 part in 10 to the 10 to the 123, that's the number of choices the creator had and so on. And then the likelihood of a solar system coming into existence by random collisions in a chaotic universe, and that being 1 in 10 to the 10 to the 60. And the upshot of that is that it would be far more likely to be lots and lots of solar systems.
Right, with chaos everywhere.
Yeah.
So that would be an instance where if you thought that standard measure was the applicable one, although it's not standard, it's canonical, use a canonical measure that Penrose uses, then it'd be an example of where it's fine-tuned for discoverability, because discoverability would be the key issue coming in there. The rest of them, you know, you get the you need the solar system to have observers, but then there's not much of the universe to see out there.
Sure.
It's like the case that, you know, there's the case that Tegmark and Reeves mentioned, the case where the universe, if the dark energy, you could, or the dark energy could be much, much larger than it is by a factor of 1,000,000. If you have the density fluctuations, a factor of 10 larger. But then they say, well, in that kind of universe, you could still maybe get life, galaxy would form, but it would be a lonely universe. You'd just be your galaxy to look out. Because it expanded so rapidly that you wouldn't see anything. So once again, discoverability, it seems there's an additional fine-tuning for the universe being discoverable in that case.
Thank you. John has some of this.
Yeah, I was just curious, you were saying, and I agree, that multiverse, it's certainly not enough to say the multiverse theory. You have to, of course, include things which include the measure problem. You have to have, you have to have not only dynamic laws, but initial state and the measure thing. But I wonder how that, because you have the same problem with a single universe, if it lasts forever, you have the same Boltzmann brain problem. So I don't quite see how you're saying how there's additional problem with the multiverse. If it's a critique of the multiverse problem, it's also a critique of the single universe problem.
Well, the critique is that the multiverse doesn't explain the actual fine-tuning that's there. That's the main critique. Okay, and to do that, you need a positive measure. Now, there's this other Boltzmann brain problem that arises with the standard measure of how the universe is expanding. Well, I'd say as a theist, Boltzmann brains aren't good things because they're these isolated, chaotic experiences. So either that sort of materialism depends on the supervenient view. So those fluctuations will actually be conscious. So you have to buy into a certain view of the mind. So either that's false, or God has arranged things or something else that keeps the universe continuing to expand forever. So it would make a positive prediction. The theistic view would make a positive prediction. There's some other factor that is not going to expand forever and produce these Boltzmann brains.
But I think most people, I mean, maybe Harlow, most people agree that our theory should make it so Boltzmann brains cannot dominate the operation. So I think, most of them think that, we should find a theory that, and I'm just saying that's a challenge for both single universe theories and multiverse theories. It may be a little different challenge, but it's not qualitatively different.
But multiverse theories have built in, the current ones, is other universes are infinite. So they already have the problem built in, but the theist need not build it in.
Ours seems, now of course you might question whether it's really a cosmological constant, but if ours does have a positive cosmological constant that stays constant, and let's suppose it doesn't decay because if it decays, then it's like the Proof's multiverse. So let's
doesn't need to commit either that, that's going to happen, or, but the supervenience piece, the typical multiverse ends up committing to all this other stuff. That's part of their construction. That's the problem.
Right, so what you're saying, the theist could be free to postulate the universe isn't sort of,
Going to
isn't going to expand forever.
But the multiverse is not, there's always going to be universes with a high positive energy density that's going to do that. And so they're going to, by their construction, run into the problem the way theists need not. So,
Thank you. I think we have just about got to 3 o'clock. So